Okay, so hello everyone. Today I'll present to you the determination of natural frequencies and mode shapes, prepared by yours truly, Robert Brand Parocha. Next slide is the introduction. The computing of the natural frequencies and modes by solving an n degree polynomial equation can be deduced. In this chapter, we shall consider the several other methods. These are the Dunkerley's formula, Rayleigh's method, Holzer's method, matrix iteration method, and Jacobi's method. So first is the Dunkerley's method. For the trivia, the author is known as the Stanley Dunkerley, born in 1870 and died in 1912. He is a professor at the University of Michigan. That books he authored is Mechanism and Hydraulics. He also created the Dunkerley's formula. Okay, the Dunkerley's formula gives the approximate value of the fundamental frequency of a composite system. It also considered the following general end of the degree of freedom system. This this one on the equation left side. And also for a lumped mass system with a diagonal mass matrix, the equation becomes this one. Next page is by expanding from equation 1. And from equation 2, we have this one. Therefore, we give this as the final equation of the Dunkerley's formula. That can be written also as below. Next is Rayleigh's method. Another trivia, he is a Lord Rayleigh, or also known as the John William Strutt. He came from a royal institution of Great Britain, London, United Kingdom, and one from Nobel Foundation. First is the Rayleigh's principle. So what is the Rayleigh's principle? Rayleigh's principle is in the fundamental mode of vibration of an elastic system, the distribution of kinetic and potential energy is such as to make the frequency a minimum. Therefore, it is the kinetic and potential energies of a n degree of freedom discrete system shows that these equations below. It also assumes the harmonic motion to be uh, in mode shape, and the fluctuation is the natural frequency. This is the maximum kinetic energy formula, and then the maximum potential energy formula, which is the maximum volume and maximum torque. This also gives us the fluctuation squared formula. That formula is also a Rayleigh's quotient. So next is the Rayleigh's quotient can be used to approximate fluctuation, selecting a vector x and substituting into this formula. It is also yield into a good estimation of fluctuation squared. The closer the vector resembles the true mode of it, therefore the accurate estimated is the fluctuation. Also, we consider the fundamental frequency of beams and shafts. The fundamental static, as you can see on the figure below, there is a static deflection curve. This shows here from this point up to this point, we can see the imaginary line called the static deflection curve that is used to approximate the dynamic deflection curve that considers a shaft carrying several masses, which is not mass 1, mass 2, and mass 3. It also covers the length 1 from this point to mass 1, length 1, and each of these mass, there's also equivalent to length. So Holzer's method is an iterative method used to estimate the torsional natural frequencies. It is an approximate tabular method that covers a trial and error scheme. It is a method that gives its shapes. Next is bitorsional systems. As you can see on the figure of the shaft 1 and shaft 2, we consider the undamped torsional semi-definite system that shows also the equations of motion as below. From the equation, this gives us the summation of the harmonic motion. This states that the sum of the inertia torques of the system must be 0. Trial frequency must satisfy this requirement. Also, from the graph below, plots the torque of M sub T applied at the last disk against the chosen fluctuation. The natural frequencies are the fluctuation at which M sub T is equals to 0. We based it on the 0 point. Next is by spring mass systems. Spring mass system, as you can see on the figures above, it is part of the Holzer's method that also applicable to vibration analysis of spring mass system. So as you can see on this figure, it is also a series single degree of freedom system, which is in series. From the equations of motion, we have given this by the spring mass system, the equation also shows that the resultant force applied to the last n mass can be computed as repeat for several other trial frequencies fluctuations, and plot a graph of f versus fluctuation. The natural frequencies are those fluctuation that gives f is equals to 0. So, naipakita naman natin yung graph na yon from the previous slide. Next is the max matrix iteration method. It assumes that the natural frequencies are distinct and well separated. From the we also have the procedure, which is bulleted. Number 1 is to select a trial vector, which is currently the x1. Pre-multiply it by the dynamical matrix, which is denoted as D. And third is to normalize the resultant column vector. And last, repeat step 2 and 3 until the successive normalized vectors converge. Next slide is by convergence to the highest natural frequency, we have given the formula below. It is to select an arbitrary of x1 and pre-multiply it by the dynamical matrix to obtain an improved trial vector. That's the first step 2. Next is the sequence of trial vectors will converge to the highest normal mode x raised to n. And constant of proportionality in this case is fluctuation squared instead of 1 over fluctuation squared. Meaning to say, it is because any x is pre-multiplied by the dynamical matrix, it would lead to the largest eigenvalue. It is necessary to remove the largest eigenvalue from dynamical matrix. Next is the Jacobi's method. The Jacobi's method produces all the eigenvalues and eigenvectors of matrix D, or the dynamical matrix, which is given by the uh, D is equal, dynamical matrix is equals to D sub ij, that is a real symmetric matrix of order n by n, or n times n. The dynamical matrix, or denoted as D, has also only a real eigenvalues. There's also an exist of a real orthogonal matrix, which is denoted as R, such that uh the R itself is a diagonal. The diagonal elements are the eigenvalues, and the columns of orthogonal matrix, or denoted as R, are the eigenvectors. As you can see on this figure, it shows that this one is the orthogonal matrix that denoted as R and generated as a product of several rotation matrices of the form. It is where all elements other than those in a column and the row I and J column are identical with those of the identity matrix, which is denoted as I. Okay, that would be all of my presentation. Thank you.